So today we are learning about the ideal gas law. The ideal gas law is my favorite gas law because it doesn't need a before and an after condition the way that Boyle's law and Charles' law and Guy-Lussig's law and Avogadro's law and all of those ones need. It just tells you everything you need to know about a single gas at a single moment in time, which is just so handy for so many things. But it actually comes from all those other laws that we've talked about already. It comes from Boyle's law. And what you should notice about these laws is that Boyle's law here, its volume is proportional to 1 over pressure. And then Charles' law is volume again. It's proportional to temperature. And Avogadro's law is volume is directly proportional to the number of moles. So each of those laws are about volume being proportional to something. Because of that, I can actually combine all 3 of them into a single law. Here's how I'll do it. I'll start with volume, and I'll say that volume is proportional to each of these things. So first it's proportional to 1 over the pressure. That means pressure is in the denominator. Next, volume is proportional to the temperature. We get that from Charles' law, right? So temperature is on top. As temperature goes up, volume goes up. So it's on top of that fraction. And Avogadro's law, volume is directly proportional to number of moles. So number of moles goes on top of this fraction as well. And what we get is a nice proportionality where volume is proportional to number of moles times temperature divided by pressure. Now we can't do math very easily with proportionality. It's much nicer to have an equal sign, so that's where we're going to go next. We'll start from our proportionality. Volume is proportional to moles times temperature over pressure. And then we're going to just replace that proportional symbol here with an equal sign times a constant. Now this time I'm going to be picky about our constant. It's going to be capital R. And that's because R is actually a number, and R will be consistent for every gas. This is what's awesome about the ideal gas law. If you have oxygen gas or ammonia gas or nitrogen gas or neon gas or whatever, and you know its volume and its temperature and its number of moles, you can figure out the pressure because R will be a constant for that neon gas. Or if it's helium gas, it'll be the same R, and that number will be 8.314 every time. If we want to rearrange this just to make it look nicer, we can multiply both sides by pressure on top, on the numerator. And that's going to cancel the pressure in the denominator here. That gives us the prettier form of the ideal gas law, which is that P times V equals nRT, or pressure times volume is number of moles times the constant R times the temperature. Now let's unpack that a little bit more. Our pressure has to be in kilopascals for this specific version of the ideal gas law where our constant is 8.314. You can actually have another version of the ideal gas law with a different constant using atmospheres instead of kilopascals for your pressure, but we're going to go with kilopascals in our course. And for that, our R value or our constant is 8.314. The volume has to be in liters for the ideal gas law to work out, so make sure that checks out. N is the number of moles, it's always in moles, that one's straightforward. R is this constant, true for every gas, it's 8.314, so we're going to be able to plug that in for R right there. And temperature, just like our other gas laws, has got to be in Kelvin, so you need to convert from Celsius to Kelvin if you start out in Celsius. Let's try an example of that. So let's say we have to find the volume of 100 grams of oxygen gas at SATP. So SATP stands for standard ambient temperature and pressure. And that actually tells us both the T and the P, the temperature and the pressure of the oxygen gas, so that no one has to spell it out for you. It's actually hidden in that word SATP. If you forget what it is, just look it up. It's on the very front page of your notes package. So what are we given here? Well, we're given obviously the mass, 100 grams of oxygen gas. Now that's not quite what I want for the ideal gas law. Remember the ideal gas law is PV equals nRT. But don't be worried here. If I know the mass, I can quickly find the number of moles, which is the thing I actually want for my ideal gas law. So we're not far off. We also know the molar mass of oxygen gas, right? Oxygen has a molar mass of 16 grams per mole, or 15.999 if you want to be a little more precise. And oxygen gas is diatomic. It's in the form O2. So we're going to do 2 times the molar mass of a single oxygen. That gives me 31.998 grams per mole. Then I'm given some information because of the SATP, the standard ambient temperature and pressure. Standard ambient temperature is 25 degrees Celsius. Now to get that into Kelvin, I need to add 273.15. The size of a degree Celsius is the same size as a degree Kelvin. It's just slid up on a scale. So you just have to slide it up by 273.15, and now you're in Kelvin. Pressure for standard ambient temperature and pressure is 100 kilopascals. So we've got that too. All right, now we want to use the ideal gas law to figure out volume, but we don't know the number of moles yet. So that's what we're going to start with. We're just going to figure out the number of moles. We know the mass, we know the molar mass, so we can do this, no problem. Oh, we're trying to find volume. That's what we're looking for. All right, so number of moles will be mass over molar mass. So the number of moles of our oxygen gas is going to be the mass of our oxygen gas, 100 grams, divided by our molar mass of the oxygen gas, which is 31.998 grams per mole. When I plugged that into my calculator, that gave me 3.125 moles. All right, now I know, let's check everything off in our ideal gas law. We know the number of moles. We know R, of course, that's just the constant, 8.314. We know the temperature, that's one of our givens. We know the pressure, that's another one of our givens. We're totally ready to find volume. So let's go for it. Here's our gas law, our ideal gas law, PV equals nRT. We need to rearrange for volume, so let's divide both sides by pressure. That cancels out the pressure on the left side. We get volume is moles times R, the constant, times temperature divided by pressure. So you're all ready to plug in your numbers. Moles is 3.125. That R value is 8.314. The temperature is 298.15, and the pressure is 100 kilopascals on the bottom. Toss that all into your calculator and you should get 77.46 liters. And we figured out the volume of 100 grams of oxygen gas.